Just put your on the right degree.
Yeah. Is this good, guys?
Oh, yeah.
Yeah. It's much better.
Okay. But slightly lower than that.
Lecturer. Hello.
It's covered by the UNISA. What was
Hey,
okay.
yeah. Before we start, can I just ask something?
Yes.
Yeah, it's just about the assignment. So, yeah, can you still submit it next week on Friday?
Yes, it is extended up to 27th.
The 27th or the 29th?
27th.
27th. That means it's a Wednesday, right?
Yeah. So, coming back
Okay.
to this question, we have a linear transformation F from V to W, and V and W are finite dimensional vector spaces, right?
V and W.
Produce?
Sir, only V is a finite vector, blah, 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 finite dimensional vector space. We're unsure what W is.
Okay, so to produce a vector subspace, U of V, alright? And what is its property? Such that?
To produce a vector subspace. The subspace is closed under vector addition and scalar multiplication.
Okay.
Oh, to produce. Such that V is equals to the direct sum of U and kernel S.
Good. Remember,
But sir, if that direct sum, that's plus with the circle around it.
yes. So what is this? It means that firstly, U intersection of kernel of this must be the 0.
Yes, sir.
And every vector V in V can be written as something like this, where U is from U and P is from kernel of F. Right?
Excuse me, sir?
That's the meaning of this, right? Every vector should be, because you remember, what is, if you give me two subspaces of V, what is P plus Q? P plus Q is all
I don't know what's going on.
Huh? Such that. Right? This is all the vectors that can be written as a P element, as an element of P plus an element of Q. And you have shown that this is a subspace.
Sir, what?
Right?
So you know this little last part? The PQE sub... What
The
is that for?
subspace.
Yeah?
PQ are subspaces of V.
They subspaces of V.
Yes. Capital P and capital Q. Q are subspaces of V, and this was the definition.
Oh.
And you
The
have
definition
shown,
of a direct subspace, a direct sum of bloody blah.
I call it the sum. Okay? And then you have shown already
The subspace of V.
P plus Q is a subspace of V. Okay? Now, there is a problem here. I don't say that P plus, that suppose you take an element from R which is in P plus Q. The definition tells me, so there is a P and there is a Q in Q such that R is P plus Q. Oh, this cannot be seen, right? Okay. Let me come back.
Sir, please. Sir, excuse me.
One minute.
Okay.
Yo.
Sir?
Oh, it's still above. So,
Sir, could you please just quickly go back to the previous page?
Please go back to the previous page. Yeah.
okay?
Element of Q.
So if R is an element of P and Q, so then in P...
Not P and Q, say P plus Q. If R is an element of P plus Q, then by definition of P plus Q, there will exist a P, small p from the vector subspace capital P, a small q from the vector subspace capital Q, so that R is equal to P plus Q, right?
Okay.
All right.
Now,
Please write from the middle, not the top, because the top is cut off by the camera.
okay. Now, we are not guaranteed that this can be written in one and only one way. It could be that there exists another P prime and another Q prime such that R is also equal to P prime plus Q prime.
Okay.
Right? Now let's have a look into this. So tell me, can you see my hand here? Can you see the arrow?
Yes. No, sir, we can't see that.
Here?
Yeah, slightly slower.
Yeah.
Right. Yeah, at least below there.
Yeah. So you are saying P plus Q is R and so is P prime plus Q prime. Where you told me both P and P prime come from P and Q prime come from Q. Now let's do a little bit of calculation. So this means P minus P prime is equal to Q prime minus Q.
Why is that, sir?
Well, you just take P prime on left hand side and take Q to the right hand side.
Oh, okay, yes, sir.
But since P is a vector space, this is an element of P and this is an element of Q.
Yes, sir.
So therefore P minus P prime is a member of P and Q.
Excuse me, sir?
You told me that P minus P prime is a member of P. And you have told me P minus P prime is equal to a member of Q. So it belongs to Q also. Right?
That makes sense.
Okay? And so similarly, Q prime minus Q also belongs to P intersection Q. Okay? So now observe something nice. I can write P as P prime plus P minus P prime. Okay? See.
So why is P? Oh, okay.
But this one is coming from capital P and this one is coming from capital P intersection capital Q. Okay? So it is kind of saying that there are some repetitions. So these repetitions of expressions can happen with each member of this subspace. So for instance, I can write something like P plus Q I can write this as P plus T plus Q minus T, where T is in P plus. Okay? So you see, I can write it in several ways, in general. So, in this subspace, P plus Q, each element is written as a member of P plus a member of Q, but it can be written in several ways. Okay? Now, my question is, when is this unique? It will be unique precisely when P intersection Q, that's a subspace, and that is only 0. Okay? So the fact is, observe, and that was one of the problems. Observe, writing uniquely is possible if and only if P intersection Q is exactly the 0 space. And that is the precise situation when I write P plus Q as P plus within a circle Q. Okay? So P plus Q with a circle, plus with a circle means that I can write these elements not only as a sum of an element of P and an element of Q, but that too also unique. Okay? Now, let's come to the question that you asked me. So suppose you give me this linear transformation. You said V is finite dimensional. Okay? Let us take the dimension to be n. Kernel of S is a subspace of V. So its dimension is smaller than.
Sorry, lecturer?
Yes?
It is not written that V is the finite dimension. It is just written that F when V maps to W be a linear transformation from a finite dimensional vector space to a vector space W.
Yes. So from a finite dimensional vector space, F is from V to W, so which vector space is qualified to be finite dimensional?
Oh, yeah, now I understand. It's V, yeah. Oh.
Now, dimension of the kernel is M, which is less than or equal to N. Okay? Start with a basis for the kernel. This is the basis for the kernel.
Sir?
Yes. 1 minute.
Why?
1 minute. Now, last time we saw a method how to extend the basis of a subspace to the full space, right? So extend. Of V. So let's see Okay? Clear. Now, so C is the basis of V. Okay. Come. This one is the basis of the kernel. So, F maps all of them to 0. C1, C2, Cn minus n, this is actually, so everything in the range is obtained as an image of C1, C2, Cn minus n. Okay? Alright? So you take your U to be the span of this.
Sir?
So, 1 minute. So then you can see from the notion of a basis itself that V is just nothing else but this plus kernel of F. Because what is kernel of F? It is the span of B1, B2, Bn. Right? And this part, so you take U to be this, the rest is the span, is the kernel of F. Every member is uniquely written in this way. And you can easily conclude now, because we have taken this to be a basis, that U and kernel of F cannot have anything in common other than the 0. So U intersection kernel of F is the 0. So therefore, V is U plus kernel. And this is what I am using actually.
Excuse me, sir.
1 minute. This is what I will. 1 minute.
What you have written down is down too low, we cannot see it. After V, U plus kernel F, whatever comes after, it's nothing, we can't see anything there.
So, you can show that V intersection kernel of F is actually the 0 vector space, and hence V turns out to be this. So, I was actually using this when I proved that the image of F and the kernel of F, the dimensions is equal to the dimension of V. Yes, now question, yes.
So, you know when we use that plus sign, right, that sum of direct whatever, sum of direct sum of subspaces.
Yes.
The moment we see that on a paper, it would imply that what we just proved is true. So,
no. A plus, just a plus and a plus with a circle are different. That's what I explained here. With just a plus, these representations, there could be multiple ways to write this same R. And each time you have a member in the intersection, that gives a representation. That's what I wrote over here.
okay, sir. So can we please go through it again, just the last part?
But, in this, in plus with a circle, the writing is unique. That's what I wrote here. Writing this uniquely.
The ranking.
Writing
Oh, the writing. Oh, yes.
is possible if and only if the intersection has only the 0 vector. Okay? That's when, because if it is the 0 vector, this is 0 and this is so this one still becomes P and this becomes Q. So it's the only way that you can write it. Moreover, you can see it from here. So here P minus P prime becomes 0. Q prime minus Q becomes 0. So P is equal to P prime and Q is equal to Q prime. Okay? So writing is unique if and only if the intersection has only one member. Otherwise, you can have as many ways of writing as there are points in the intersection. Okay? So this is something nice that you should feel. And saying that saying something as a basis is nothing else but saying that the vector space is so. So for instance, when you are saying this, when you are saying something, when you are saying that C is a basis of V, what you are actually wanting to say is you look into the one-dimensional subspaces, span of V1 and so on.
Oh my gosh, I think I get it, sir.
And you take the sum, this is equal to V. Okay? So that's what you mean by saying that something is a basis. So you see, this unique form and this unique writing way is another, it's actually saying the same thing about a basis in another form, nothing else. Okay?
So when you say V is equal to V plus curl of F, that means the image of F, function F, is equal to U, element of U.
No, the image is actually, so this tells me that the image of F is nothing else but F of U. That is obvious.
Sir, can you please start again from the beginning? I got lost somewhere. I don't even know where that somewhere is anymore.
My goodness.
This question is actually.
Yeah?
Oh.
So, sir, when you say U, V is equal to U plus curl F, that's when the image of F is equal to FU. Function of F.
Yes.
Oh.
Yes.
I get it.
Yeah.
Sir, I don't get it.
Can you please, then I think we should move on. So you please write me back and I'll write you back again.
Okay, sir.
Okay. Now, let's move forward. We are already one class late, behind our schedule, and then we are in darkness, so I don't know whether we will be in further darkness next week, so I really don't know what carries on. Okay, so what I wanted to say about is, today is something about eigenvalues and eigenvectors. Yes.
Those plans evolution or Boolean evolution, the platform are using the Boolean evolution.
No, it's not a Boolean operation.
It's just a addition.
Yes, I've defined that addition also before. We'll come back to it. Now, remember, so suppose we take V to be a vector space, finite dimensional, and dimension of V is n. Now, we have seen two things over side by side. One is all homomorphisms or linear transformations from V to V. This is a vector space. The addition of vectors is given point-wise. The scalar multiplication of vectors is also given point-wise. So with these two operations, home VV turns out to be a vector space. Good. But there is something more than that. Sorry. If we have two linear transformations, their composite is also a linear transformation. Okay? And we have a very, very special linear transformation, which is the identity of V over here. Okay? Now let's look into the composite. Well, I take a pair, F and G, and I give, so I can think of the composite as some kind of a product, some kind of a multiplication. Okay? How good is it? Well, it is associative. It may not be commutative, but the identity is something like as if our one, as if, I'm saying as if, it behaves like our one, right? When I multiply anything by 1, I get it back. Okay? A times 1 is A. Something like that, right? This is A times BC is equal to AB times C. So associative. Okay? It's not commutative. And it distributes over addition. As well as the other side. Okay? So, it almost, so these things, and there's another nice thing which I forgot to mention, is F composed lambda G, is lambda of F composed G, is lambda F times composed G. So it seems that these operations are very, very similar as if, like numbers, but, well, this is only working, it's not commutative. On the other hand, we also had the matrices. The matrices, the square matrices now, with real entries. Okay? And I know how to add two matrices. I know how to take their product. I know what is lambda times A. With this addition and this scalar multiplication, it is a vector space. Okay? As far as the product is concerned, let's see, it has very similar properties, right? It is associative. It need not be commutative. I have the identity matrix of order n, and I have the multiplication distributing over addition from both sides. And I also have there's lots of similarity between these two as far as these equations and structure is concerned. And there was this nice map. So if I take a basis, say B, say MAT from V to B, okay? It was taking a linear transformation to its matrix and so on and so on. This was a bijective linear transformation. Okay? So now, the whole question comes here that we have given two linear transformations from V to V, we can add them. We can multiply them by a scalar. We can multiply two linear transformations even. It is actually the composite. And the multiplication is very nice in the sense that it is associative. The identity is the identity element of that multiplication. The multiplication distributes over addition, okay, and so on. What can we do with this? Let's see. Suppose I am given a linear transformation. So I have f. I can add f to f, which I usually call 2f. Okay? I can add f to 2f, which I call 3f. Okay? And similarly, if I know what is n minus 1f, I add f, I get nf. And it carries on. Okay? There's no problem with this. On the side of matrices, I have a matrix A. I can add two matrices the same. Then 2A plus A is 3A and so on. See the parallel. Okay? Yes.
So now, the composite functions that are as a result of linear transformation, they share the same properties with the matrices. By virtue of them sharing the same properties, is that the reason why we relate the two?
Yes. Yes. And the matrices, the matrix of a linear transformation is the key, going back and forth, right? Okay. Now see, this was with addition. We can look from the perspective of multiplication also. F composes F, we shall write this as F squared. Right? What is X squared? What is it? Think of numbers. What is X squared? X multiplied with X. Right? Here our multiplication is composition. So F composed F is F squared. Right? F squared composed F is F cubed. What is X cubed? X squared times X. So see, we can as if blindly carry on doing what we did with numbers. F to the power n minus 1 composed with 1 with F is F to the power n. One thing, we define F to the power 0 to be the identity. This is what we put as definition. Okay? Then, once we put this, then everything seems like as if we are doing numbers. Okay? See, the same thing happens with matrices. A, what is A squared? A times A. What is A cubed? A squared times A. And what is A to the power n? A to the power n minus 1 times A, and so on. And A to the power 0 is again, we know, defined to be the identity matrix. Yeah?
Sir?
Yes.
The right-hand side is matrices and the left-hand side is?
Linear transformations from V to V.
Okay, so we're showing similarities between the two.
Yes. Yes, now I'm going to say much more. So now suppose we had this polynomial. Okay? Suppose we had this. We can think of 2 times 1v plus 3 times f plus f squared. Yeah? This is again a linear transformation. Clear? F given f square is 3 times f is 2 times the identity is, so their sum is. Okay? So this is again a linear transformation, which I will write as PF. Okay? So in general, for any polynomial QX, there is which is again a linear transformation from V to V. And you know how to get hold of it. Okay? Similar picture over here. So you can write 2 times In plus 3 times A plus A squared. Okay? So in general again, for any polynomial here, there is the matrix. Okay? Clear? So you see how rich both these structures are. And the nicety about this is exactly a copy. Whatever can I say with matrices, square matrices, can be said about linear transformations. And whatever can I say about linear transformations, I use the matrix again to go back and forth, okay? So one thing can be said in terms of matrices or in terms of linear transformations. Okay. So now let me say, what do I mean by an eigenvalue? Okay? What, yes? Yeah, what is meant by an eigenvalue of a linear transformation, or side by side an eigenvalue of a matrix? Okay? Clear?
So we're looking at eigenvalues with respect to linear.
Sorry, can I please just quickly ask?
Yes.
Based on everything we just did right now, it implies that every matrix transformation is a linear transformation, right? And every linear transformation is a matrix transformation.
Well, we did this long back. Whenever we took any linear transformation, we have found the matrix for that linear transformation, right? Conversely, and that matrix was obtained by considering specified basis for the domain and the codomain. Okay? Conversely, if you give me a matrix, then taking the usual basis on the domain and the codomain, because if it is n cross n matrix, it will be a linear transformation from Rn to Rm, and taking the usual basis on Rn and the usual basis of Rn, we know how to find the linear transformation whose matrix is that given one. Okay? So, matrices are nothing else but linear transformations. That was what we knew before we entered today. Okay?
So can I please ask, so we knew that before we started this, so then we're doing this based on that?
Yes.
Oh,
yes,
okay.
Exactly. But what I'm trying to say is there's something more here. Because we are considering vector spaces from V to V only, vis-a-vis matrices which are square matrices, we can not only add and scalar multiply them, but we can also multiply them. Okay? So multiplication now comes in as a binary operation, again another binary operation. You take two matrices of order, square matrices of order n, multiply, you get a square matrix of order n. So it's a binary operation.
Sorry,
You
sir.
take two linear transformations from V to V, you compose it, you get a linear transformation from V to V.
Excuse me, sir.
Yes.
Now, how does one show that with the usual addition and scalar multiplication of matrices, the Eugene vectors, or is it Eugene vectors or something, of R is a finite dimension vector space, and the dimension of the Eugene vector is equal to Mn?
Wait, I have not come so far.
Okay.
You are galloping.
Sorry?
I have
Yes,
not
sir.
come so far, you are galloping.
Okay, right.
Okay. Okay? So that is something new now with square matrices. We can add them, we can scalar multiply them, we can also multiply them. And the same thing on the side of linear transformations from V to V. And that is one of the reasons why linear transformations from V to V are also given another name. They are often called endomorphisms. The word endo means onto itself, and the word morphism means change. Okay? So it's often also called endomorphisms. It's a change onto itself. Okay? V to V. All possible linear transformations from V to V. Okay? That's another name. If you don't want the name, forget about it. Just think about it as linear transformation from V to V. Okay. Now,
Before you move on, I just want to mention something. You said that multiplication of linear transformation is a composite function, and you just
is the composite of
yes,
it. Yes.
it's a composite function, and you just highlighted that only if we are dealing with endomorphism.
Yes.
So what if we have any homomorphism?
Good. So, if you have a morphism from V to W,
Yes.
and if you have a morphism from W to P, the composite is from V to W. It's not from, so the set has changed.
Okay. So these properties you are associative, they still apply to you.
Yes, very much correct. The composition is still associative. The composition still distributes over addition, and from either side everything holds good. But what is the magic? The magic is no more a binary operation. Okay? Because the sets change. Okay? But the moment all of them are V to V, it becomes a binary operation. That's the magic. Okay? So the magic is just there. Right? So that's the extra magic that we suddenly have by taking V as the domain and the codomain also. Okay? See, the same thing was true for matrices. You take n cross n matrix and take an n cross p matrix. You can multiply it. Okay? You get an n cross p matrix. But one was an n cross n matrix, the other one was an n cross p matrix. You get an n cross p matrix. So you are getting two sets. So it's not a binary operation. Remember, binary operation means it has to be a map from x cross x into x. Okay? Now when you take your m cross n and so on to be squared, so it's n cross n times n cross n, it's again an n cross n. So suddenly it becomes a binary operation. So that's the extra thing that I'm saying. Okay? You just, by taking this product, you don't go outside. You're still there in that same vector space. Yeah? So that's the extra thing. Okay. So now let's come to the definition of an eigenvalue. What is an eigenvalue? So you start off, so suppose V is always finite dimensional today. Okay? And lambda is a real number. I will say that lambda is an eigenvalue of it if. Now, wait. Just a little bit. F is a linear transformation. Identity of V is also a linear transformation. Lambda times identity of V is also a linear transformation. So we have seen this. And F minus this in a linear transformation. Yeah? And we can speak about this. The kernel. Okay? Remember what's the kernel of a linear transformation? Everything which is taken to zero. Right? So I can speak of this. So this is a subspace of V. I'm saying this subspace is not the zero space. Okay? That means, what does it mean? What does it mean? So, it means that there is a vector V. V is non-zero such that F minus lambda of V is not equal to zero. Sorry, sir. I'm sorry. So that is there is a non-zero vector which is inside the kernel. Right? Now let's look into the definition of this. This is pointwise. So this is FV, and identity of V is this. So this means okay? So it means that there exists a non-trivial solution of Fx equals to lambda times x, or Fp is equal to lambda times x. Yeah? That's it. And any vector which is non-zero is an eigenvector of F corresponding to the eigenvalue lambda. Okay? So there is only eigenvalue. Eigenvalue is a scalar. You can have an eigenvalue of a linear transformation, and each eigenvalue gives you some non-zero eigenvectors. Okay? So what are the eigenvectors? Nothing else but the kernel. Okay? And that is another name of that is called the eigenspace of lambda. Okay? So another symbol for this is the eigenspace of this, like this. Okay? E. Okay. Now let's look into it from the side of a from the side of matrix. So it's almost similar. Lambda is an eigenvalue of A if kernel, again the kernel, so I just write this if there exists X Rn This is what you usually get hold of in your books, okay? And this X this is the eigenspace of lambda or eigenspace of lambda and the eigenspace of A for lambda, and eigenvectors are the non-zero members. Okay?
Sir?
Yes.
I'd just like to make sure that an eigenvalue just basically, like after going through the transformation, it simply dilated, or it went out, like it's the same vector, it just stretched out or it stretched in.
Correct. If there exists one such, it is not known, it is not true that any scalar will be an eigenvalue. Okay? But if there exists one such, then you are saying, see, there is another way of viewing this. So, what you are trying to say, okay, this alternative view, I'll rather write it in an answer. Please send me your query and I'll write it back. It is saying about invariance and so on, but I think I'll take a little more time and I'll go away from the focus, so I'll better write it as a separate answer. Okay? So please send me your query. Yes.
I just want to make sure that I'm understanding though. You see where you wrote xu minus lambda equals 0? Yes. So this is my understanding towards this. Please tell me if I'm correct. Since we are trying to define eigenvalue with respect to linear transformation. So once you said, what I thought was, so if we can prove if we can prove the existence of scalar multiplication, then we can prove that there exists
Scalar multiplication is always there, right?
Yeah, but I'm saying lambda and
Yes. So you want to have a non-zero thing over here. So actually what you are trying is computing this kernel. Right? Given this linear transformation, what would you do? You take a lambda. Say you take lambda equals 2 to check whether 2 is an eigenvalue or not. So you look into f minus 2, that particular linear transformation. Look into its kernel. Okay? If its kernel is 0, that means 2 is not an eigenvalue. If its kernel has a non-zero vector there, then that is an eigenvalue. Then 2 is an eigenvalue. Okay, that is what I'm saying.
Sir?
Yes.
Can I please ask, why did we specifically use F minus lambda 1V?
Boils down again to your same old question. And I would rather answer it as a separate note. Okay? So, it is more about this geometrical representation, a kind of a picture. I can understand you are just missing this picture, you are trying to get hold of this picture when you are saying if V is lambda times V. So, yes, you're right. In a sense, I'm trying to say that if lambda has an eigenvalue, then there are certain vectors on which F acts like as if it is being pointing to that same direction, but the magnification changes. You're absolutely right. It's only for those things that I'm looking into it. Correct. But there is, I need to make this a little more pictorial, and I'll do so. You please send me your query, I'll do so in a much detailed write-up. Okay? Just let's now look into a few follow-ups of this notion. Clear?
Yes, sir.
Okay. So, now, the question is, does every linear transformation, so you gave me V to V, okay? And V, you only gave me these finite dimensions. Say the dimension of V is n. Okay? You give me this only. Now the question is, does F, nothing is given. Just this, that it is a finite, on a finite dimensional vector space, it's a linear transformation. The question is, does it have an eigenvalue? And the surprising answer is yes. Yes. And how do I get it? Okay, so here is the way. Take any V from V such that V is not equal to 0. Okay? Now look into this list. How many vectors are there in this list?
Infinite.
Huh?
Infinite.
Infinite.
No, not. How can it be infinite?
N.
N?
Yes, sir.
Suppose.
Oh no,
How
the
many
N
are
plus
there?
1. 3.
So how many are there?
N plus 1.
There are n plus 1 vectors.
Because it's U echelon. That's 3. So then it's 2 plus that U.
Come on, it is simple. 0, 1, 2, 3, 4. If you start your counting from 0 up to a certain number, how many? 0, 1, 2, n. How many numbers?
N plus 1, sir.
Yes, that's it. So there are n plus 1 vectors. Now, we have n plus 1 vectors in an n-dimensional vector space. So what happens? What happens? We have n plus 1 vectors in an n-dimensional vector space. What does n-dimension mean?
Oh, so doesn't that mean that one of them will be dependent?
Correct, it means, not one of them, it means that this is a dependent list. Okay? In an n-dimensional vector space, so it is linearly dependent. So hence, there exists scalars such that yeah? So this means using my operations okay? Now take Px to be this polynomial. So Pf at V is 0, which means that V is in kernel of Pf and V is non-zero. Okay? Remember, Pf was a linear transformation also. So V is in kernel of Pf and V is non-zero. That's what we have proved till now. Okay? Now, this is the first time that I am going to refer to complex numbers. I will be using certain facts about complex numbers. I believe all of you know what are complex numbers, right? Those are numbers which can be written as a plus ib, where I squared is minus 1. A plus ib, the number a minus ib is often called the conjugate of that number. And you know similar many other facts for complex numbers, its modulus, argument, and so on. We will not read all of them, but okay. But something nice we are going to see now. So this is a little bit of a digression